Okay, guys, this is section 3.3 in your textbook. It's starting on page 128. This section in your textbook, there's a lot of exercises with geometry or sketchpad, which we're not using, and then a couple of exercises with a piece of paper, which I would like to use if we have time. So we actually fold up a piece of paper to demonstrate some of these properties. But for the sake of time, I'm going to review it algebraically and on the board here. Before I do, though, I'm going to do a quick review of just some of the different shapes that you guys should know already, but there's a few definitions in the book here that you just might need a little bit of refreshing on your shapes. So you can find all these definitions in the glossary at the back of the book. The first one is a polygon. We know as a polygon is any two-dimensional closed figure whose sides are line segments. Okay, so any of these shapes would be considered polygons. Okay, square, rectangle, triangle, trapezoid, any of those. Quadrilateral. So check the prefix of the word quad. We know means four, right? So it's a polygon that just has four sides. So it doesn't have to be a square. It could be a different shape as long as it has four sides. It could be any strange shape. That's a quadrilateral. Okay, and I bring up those two definitions because we need to know, for the purpose of this section, what a parallelogram is. And most of you do already know this, but it's a quadrilateral, so it has four sides with two pairs of opposite sides that are parallel. So the opposite sides are parallel. Typically, we know a parallelogram looks like this. But it can look something like this. It can look strange in its own way. As long as the opposing sides are parallel, that's also a parallelogram. And finally, a trapezoid. It's a quadrilateral, so again, four sides. Quad is four, with one pair of parallel sides. So typically, we always see it like this, but that is also a trapezoid, believe it or not. Okay, it can have a very strange looking shape. That's also a trapezoid. As long as two sides are parallel, the other two sides can really go in any direction. Obviously, they still need to close the figure, but that's about it. Okay, any questions on the different shapes? Yeah?
Is a square still a parallelogram?
A square, yes. Two sides that are opposite, and it's a quadrilateral. Yes. Good. And they're both parallel in a square. Yeah. Okay, number key concepts I'm looking at. So I'm kind of skipping towards the last page of the section. This is on page 134. You can see your key concepts there at the top. The first one is the diagonals of a parallelogram bisect each other. Okay, so I actually kind of went to prove this. Not necessarily, you guys need to understand this process, but you won't necessarily have a question fully like this. So this is a bit of a proof, so you're going to need to understand how I derive this, but basically at the end of this, you just need to know this key concept. Okay, so that's the idea. So this is kind of, it gets a little complex just because my numbers weren't perfect. I just chose random numbers, but just trying to follow it through with me. So I'm saying the diagonals of a parallelogram bisect each other. So what does bisect mean? We talked about this before, yesterday. What does bisect mean? Come on, guys. Nobody? Henry?
It split the shape into two sections, I guess.
Yeah, that are, so when something bisects, it splits into two, right? But typically those two sections are, Tiago?
Equal?
Yeah, they're equal. Good. Excellent. So when we're saying the diagonals of a parallelogram bisect each other, what we're actually saying, so here's the parallelogram, the original parallelogram, right? Two sides, opposing sides that are parallel. So there's this side and this side and this side and this side. The diagonals, we call the diagonals, are just the diagonal lines that cross inside the parallelogram. Those are the diagonals. And what I mean by they bisect each other is I'm saying that because they're crossing right through the center of each other, these sides are equal. Okay? So it's important to know. So not necessarily this side is equal to this side. Okay, make sure you understand the difference. These two sides are equal and these two sides are equal, but not necessarily this side is equal to that side. That makes sense? Because these are different lines. Okay? So when a line bisects, it's dividing that line into two equal parts. So these two sides are equal and these two sides are equal, not necessarily this side and this side. Although this parallelogram looks that way, if I were to do it on a funny shaped parallelogram, that also looks kind of the same. But you can see that this side here is much longer than this side here. Okay, do you see that? So it's important to understand that the line bisects itself, those two sides are equal, and these two sides are equal. You see that? There's no way that this side is equal to this side. But in the diagonal itself, it bisects the middle point. So these two sides are equal. Okay? Any questions there? That's the only kind of area I can see you getting confused. Follow with me. I'm going to go through it quickly. There's nothing new here. It's just kind of a lot of math. So I want to first find the intersection point. Okay, so this is to prove what I've just told you. Okay, so I want to prove that this line AI is equal to the line IC, or I can prove that AI is half of AC. Does that make sense? It's the same proof, correct? If I prove that this is half of this, then I know these two lines are the same, right? Okay, so the first thing I need to do then is to find the slope of these two lines so I can develop an equation for this line, equation for this line to get the intersection point. Okay, you guys should be familiar with that, right? So we're finding the slope first between B and D. So that's 0.11 and 0.45. So I plug in the slope. I find out the slope is 4/3. I use that slope then to plug into my formula for a line. And then I use also a point on that line. I'm using point D because it's a simple 0.11. So I use the 0.11 and sub that into the equation of a line to solve for B. Okay, once I have B, I can then find my equation of the line, which is here. So this is the line BD. Okay, any questions there what I did? Again, this is a bit of a review from chapter 2. Okay, so I have my equation of line BD. To find this intersection point, what's the next thing I need to find out, Stephen?
Oh no, I was going to say, couldn't you just find the midpoints of both ED and AC?
You could, but that's assuming the proof. So I think it was, Matthew asked me about this yesterday, and so did Luigi. They found a shortcut in to find, I think it was about the centroid. But they're assuming the proof already. Do you guys see the problem with that?
Whatever then if they're the same, then you know the proof is true.
When you're finding the midpoint, if you find the midpoint of this line
Yeah.
and the midpoint of this line, if they're the same point, yeah, okay, that could be one way. But you can't assume that it's the midpoint before checking the lengths. Okay? First of all, but that's one way you could do it. If it's the exact same point, then you know that it would bisect them. Yeah, good, that's another way. All right, so we have the equation for the line BD. Likewise, I'm going to find the equation for the line AC now. So I find the slope of AC using our slope formula. I plug in the slope to equation of a line, solve for B, find out my equation for line AC. So this is line AC. Okay, once I have those two equations here and here, I can set them equal. That's what I'm doing right here. So just setting by substitution, y's are equal, so this side is equal to this side, so 4/3 x minus 1/3. And it gets a little bit messy with the fractions, just because I chose random points, so it's not nice and neat with whole numbers, but eventually I work out and I find my x value is 2.5. Okay, and that's just by collecting like terms over here and rearranging. Once I have my x value is 2.5, I can sub that into either equation. I chose to use the line BD equation, and I solve for my y value, which is 3. Once I have my x and y value, then I have my intersection point between the two lines. Okay? Once I have my intersection point, I'm going to check the length of the line AC. Okay? So to check the length of the line AC, we use the length formula for a line, and I solve its root 29. So again, a bit of a messy number, but then I check the same length of my AI now, point from A to I, and I find out that it's root 7.25, and then if you use a calculator, you can see that this value is exactly half of this value. So therefore then, this line is half of this line. I know my intersection point between the two lines is bisecting my diagonal. Any questions there? No questions? Okay, so there's a couple more concepts. So again, kind of a bit of a long, messy proof, but you just need to be responsible for kind of the end result, and that is knowing that the diagonals, they bisect each other into two equal sides in a parallelogram. Okay, don't think that happens with a trapezoid, because it's very different with a trapezoid. You could have a trapezoid that looks like, you know, this. Okay, this is a trapezoid now with the diagonals, and you can see very clearly that the diagonals do not bisect each other. Okay, so don't get that proof confused. It's only with parallelograms that the diagonals bisect. Okay, the second point, this is point number 2. Okay, so this is an interesting one. And I underlined the word any, which the textbook doesn't, but I want to make that clear. Joining the midpoints of adjacent sides of any quadrilateral forms a parallelogram. So let's just draw a bunch of quadrilaterals here. Okay, so I've drawn all random quadrilaterals. The midpoints of adjacent sides. So any type of quadrilateral, we'll draw a nice even square as well, or rectangle. So I'm going to join the midpoint. So here's the midpoint. Okay, so interesting. You can see here, no matter how funky the shape gets, you still draw a parallelogram every time. Okay, and we could go through the whole effort of proving this out. Who can tell me how we would prove this? Okay, how would we prove this? Yeah, Michael.
You would find the midpoints of all four, and then
Yeah.
you would find the slopes.
Good, exactly. Very good. So we would just find the midpoints, all four, and then find this slope, see if it's the same as this slope, find this slope, see if it's the same as this slope. Okay? Do we need to go through that exercise? Are you guys pretty clear on that?
We're good.
We're good.
Pretty clear? Yeah, it's a lot to show, but you can also see from the drawings, it's pretty clear, right? What's happening here. You join the midpoints of any type of quadrilateral, so any shape that has four sides, any polygon with four sides, and you get a parallelogram. Okay, that's then the last point we're going to make for this section, point number 3. So it's a long one. It's in the book on page 134 already, though. The line. So if I'm taking the time to write this on the board, you should be taking the time to write it in your notebook, right? Okay, long, little convoluted point here. We'll go over here. Looks like this. What does this mean? The line segment joining the midpoints of the non-parallel sides of a trapezoid is parallel to the parallel sides and has a length equal to the mean of the lengths of the parallel sides. It's a mouthful. Anybody have any idea what this means? Other than just rereading it? Kyle?
The midpoints of the non-parallel lines in the trapezoid are parallel to the parallel sides.
Yes, you're right. Yeah, good. You put it in your own words. Very good. It's going to help if we have a drawing here. I'll do a typical trapezoid, but I'm also going to show a strange trapezoid. Trying to make it stranger. That's all I can get. That's all I got. Okay, so here's my two trapezoids. I'm going to try and kind of get an idea or prove this proof, so to speak. So it says the line segment joining the midpoints of the non-parallel sides. Okay, that's easy enough. So the non-parallel sides are these sides. So the midpoints of the non-parallel sides are here, and these points are non-parallel. Okay, so the line segment joining them. So I'm going to join that, and I'm going to join this. one pair of sides is parallel to the parallel sides. So it's saying that this line segment joining the midpoints is parallel to the parallel sides. That makes sense because it looks right. Okay? And has a length equal to the mean of the lengths of the parallel sides. So what does that mean, Michael?
You add up the parallel lengths, divide by 2, it equals the length of the midpoint.
Very good. So if this is my shape here, A, B, C, D, E, F, what the key point is telling us then is the length EF is equal to AB plus DC divided by 2. That's the key. Okay? That's what you guys need to know. That's what this point is telling us. Yeah, Gianluca?
What about like if it's another way around? So let's say you have EF and you have DC, how would you get like AB?
Yeah, very good question. That's one of your homework questions. Excellent. So you want to know, say that again? You wanted to know which one?
Let's say you have the value of EF and DC, how would you get AB?
Good. So let's say AB is the unknown, right? Let's just give these ones some values. So let's say EF is, I can't do that actually because they'd have to be accurate numbers. So you want to know how to find AB, so we can just use math and work this out. So EF, we want to isolate AB then. So we need to multiply both sides by 2, right? This side and this side by 2, so the 2's cancel here and a 2 goes here. So it's 2EF is equal to AB plus DC. You follow that so far? So now 2EF, we're going to minus DC. DC is equal to AB. Okay, so that's how you find AB. If you knew the length of EF and DC. You get it? Any questions there? Good question though, because that's part of your homework. So again, the same idea here, if we label these A, B, C, D, E, F. So a little bit different labeling. But the length of the line EC then is equal to AB plus DF divided by 2. Okay? And the proof for this, so that's the concept you want to know. The proof, which you not necessarily will be responsible for replicating, is on page 133 at the bottom there. Okay, that's the proof. It's not very long, but it can get a little confusing. I won't have you guys be responsible for knowing how to prove it. You just need to know how to use it. Any questions? All right, that's the end of 3.3.